going to be talking about some work based on these papers with my advisor, Hongyu. And mostly I'm going to be talking about this first paper, and hopefully towards the end I'll get to connections to some work from these earlier papers. Okay, so let me just start with some very general background about thermalization and unitarity and the context of the question that we'll be interested in. So quite generally, we expect that if we have some interacting many-body system, and it's not an integrable system, then if we start from some generic initial state, it should almost always evolve to an equilibrium state at late times in some sense. So we'll be interested in this question in quantum mechanics. So we'll consider some quantum many-body system, which is initially in a pure state psi 0. And then we know that, as always in quantum mechanics, we can find the time-evolved state by just acting on this with the unitary time evolution operator for this system. Okay, so in this context, equilibration means that in some sense, this time-evolved state, psi of t, should macroscopically resemble some kind of equilibrium density matrix, rho equilibrium. And in particular, this macroscopic resemblance means that if we consider some generic few-body observables O, then we should find that the expectation value of the observable in this time-evolved state is close to the value in the equilibrium density matrix. Okay. But in quantum mechanics, we have certain kinds of constraints. So in particular, under unitary time evolution, we know that pure states can only evolve to pure states. So this density matrix for the time evolved state cannot actually become equal to rho equilibrium, which is some mixed state, right? And one type of observable which can distinguish between pure and mixed state is the set of Renyi entropies. So for this, we just find the reduced density matrix of the time evolved state in some subsystem A of the full system. And then we can take the trace of powers of the reduced density matrix to find the Renyi entropies. In particular, the limit of this expression as n goes to 1 is the von Neumann entropy, which many of us are very familiar with. So in a pure state, for any n, we should find that for any subsystem A and its complement A bar, each of these Renyi entropies are equal, okay? And this is not true for a mixed state like rho equilibrium. So then the question is, if these are observables which somehow know that rho of t is not actually equal to rho equilibrium, then at late times when the state has equilibrated, in what way do they simultaneously capture the physics of both equilibration and this constraint from unitarity? Okay, so what form do these Renyi entropies take in this macroscopically equilibrated state? So calculating the Renyi entropies of such a time-evolved state in a many-body system and in a way that's consistent with unitarity is always an important question in any system. But this has been a question which has been considered to be of fundamental importance in the context of black holes. Okay, so why do black holes fit into this question? So we can imagine that roughly the picture of black hole formation and evaporation looks like this. We start with some isolated star, which is in a pure state psi 0. And then the star collapses to form a black hole. Okay, and then later this black hole radiates, and often this radiation causes the evaporation of the black hole. But black holes behave like thermal states in many ways. So in particular, they can be shown to emit thermal radiation, and they can be associated with a certain temperature at which this radiation is emitted. And they can be associated with an entropy which satisfies standard thermodynamic relations involving this temperature. And we can also look at correlation functions of few-body observables in the presence of black holes, and these will also take thermal values, okay? So in many ways, they resemble thermal states, but if we assume that whatever laws govern quantum gravity are still consistent with the unitarity of quantum mechanics, then even though there's this resemblance to a thermal state, a black hole should still be a pure state at late times. Okay, so it should be an example of this type of equilibrated pure state that we've been thinking of. So this means in particular that if at late times when the black hole is radiating and the full system consists of the black hole and its radiation, then we should have that all the Renyi entropies of the black hole are equal to all the Renyi entropies of the radiation. Okay, and this should be true at all times. But it's not exactly clear how this should be calculated in gravity systems. And several decades ago now, a semi-classical calculation was done by Hawking. And it was found that according to this calculation, it seems that the Renyi entropies or the entanglement entropies of the black hole are not equal to those of the radiation at late times. Okay, so this was the famous information loss paradox of Hawking. And the key question here is, how can we obtain a unitary result for the entanglement entropies of an evaporating black hole? Okay, and in our, for us, this question is an example of the question that I mentioned earlier of how you can find a unitary result for the entanglement entropies of any system where you have a thermalized pure state.
Shreya,
okay.
Can I just ask a basic question? A bit more about my ignorance of how black holes are formed. So if you're saying a star collapses into a black hole, is that process possible without having to necessarily eject material? Like you can really think of the black hole as being the, the whole system afterwards?
No, so you have, so the star collapses to form a black hole, and that process doesn't need anything except for the star itself. But then after the black hole is formed, in general, it will radiate, so it'll emit radiation. So the full system consists of both the black hole and its radiation.
Sure, so, yeah, I understand that part, but I mean, even to get the black hole, you don't you need, like this whole supernova business, etc., to like blow away material? Or there are solutions where you just literally get the whole star becomes a black hole. Is that what you're saying? Those solutions exist?
Yeah, so you can write down a form of the metric where initially, like you can write down these Vebia metrics, etc., where you initially just have a space-time which doesn't have a singularity in it. And at late times, you can see that there is so at initial times there is no horizon, and at late times you can see that a horizon is formed. And this doesn't. You can have very simple models for this, which don't need a lot of details about the astrophysics.
Thank you.
Yeah. So for us, we're not really interested in the details of how this process occurs. We're just kind of interested in the fact that somehow you have some initial state, it's pure, and then you have a black hole which behaves thermally. So how can you find the entanglement entropies at this late time? So we're considering a very abstract version of this process. Okay, cool. Any other questions at this point? All right, cool. So some progress towards answering this question was made also several years ago. And to do this, this set of papers considered a very general setup where you had some system, some full system L, which could be decomposed in any way into two subsystems, A and A bar. And then the calculation that was done in these papers was to consider all possible pure states in the combined system, in the full system L, and average the entanglement entropies of the regions A and A bar over all such pure states with the uniform measure. Okay, and so you can find some general result, but in the particular case where one of the subsystems is much smaller than the other, you have a particularly simple result, which takes this form. So for all the Renyi entropies, the Renyi entropy of A is equal to the Renyi entropy of A bar, which is equal to the minimum of the log of their dimensions. Okay, so this is something that's manifestly symmetric in A and A bar. And if the dimension of the full Hilbert space is large, then you can also show that the standard deviation about this average is very small. Okay, so this means that if you take some random pure state or some typical pure state, then you have a very high probability of just having exactly this value of the Renyi entropies. Okay, so two very good things about this result are that firstly, it's manifestly consistent with unitarity in the sense that it's symmetric in A and A bar. And secondly, in this case where dA is much smaller than dA bar, the value of SNA is the same as the value that you would get from a thermal state at infinite temperature. Okay, so this gives us some hint of what kind of expression we might need if we want to capture the effects of both thermalization and unitarity. But it's not clear, one thing that's not clear is how to generalize this calculation to cases with finite temperature and to cases with infinite dimensional Hilbert spaces. So if you have an infinite dimensional Hilbert space, a similar average to this higher average doesn't really exist. And also if you have a finite temperature case, then it's not clear how to show how this expression generalizes. And another thing, that even if we consider this specific case of finite dimensional systems which thermalize to infinite temperature, then even if this average gives us some kind of leading order behavior for the entanglement entropies at late times, it's not clear how to systematically improve this result that's obtained from averaging. So we would like to find some kind of systematically improvable approximation for these quantities, even in these simplest examples of systems. Okay. So the plan for the talk will be to derive an approximation method for finding entanglement entropies in equilibrated pure states. So I'm going to outline some of the steps of this derivation. And this will be a method that in particular addresses these issues that I mentioned on the previous slide. So it's applicable for finite temperatures and infinite dimensional Hilbert spaces. And in principle, we can try to systematically improve it. And I'm going to talk a bit about the general mathematical structure and physical implications of this result. And then I'm going to talk a little bit about the applications of this to the black hole information paradox. And hopefully, if there's time at the end, I'm going to talk a little bit about how to understand this whole picture from an operator evolution perspective. Okay. Great. Are there any questions so far? Okay. Great. So now I'm going to spend the next few slides just developing this approximation. So our starting point is that we can identify, we assume that we can identify some equilibrium density matrix, rho equilibrium, which our time evolved state will resemble at late times. Okay, so this equilibrium density matrix will in general have some form like this, where I alpha is some effective identity operator and Z alpha is like the partition function, which also captures the effective number of degrees of freedom. The effective dimension of the Hilbert space, which can be accessed from the initial state. And we'll assume that in everything that we do, we'll assume that this effective dimension of the Hilbert space is very large. And one thing that's always true for these equilibrium density matrices is that I alpha is invariant under the time evolution. So this is almost a requirement from saying that it's an equilibrium ensemble. So under the action of U, it stays invariant. And some concrete examples of this are, we can take I alpha to just be the identity on the full system. So in this case, this effective dimension is just exactly the dimension of the full system. And we can also consider the microcanonical ensemble, where we pick some energy E, and we consider a small interval around that energy, and then we just consider an equal mixture of all energy eigenstates with energies in that interval. And we can also consider the canonical ensemble for some e to the minus beta h, where this temperature beta is determined by the expectation value of the energy in the initial state. So which choice of ensemble we make has to be physically motivated by what our initial state is. So for example, the infinite temperature state might be relevant, the infinite temperature ensemble might be relevant if our initial state, if there weren't many constraints for where you could go in the Hilbert space from that initial state. So for example, if there was no energy conservation in the system, then this would be an appropriate choice. For the microcanonical ensemble, this seems like it would be an appropriate choice if the initial state has a very small spread in energies, whereas the canonical ensemble should apply if you have some state which has a wider range of energies in it initially. Okay. So you have to make some physically motivated choice of which rho equilibrium you want to associate with your late time state. So now to actually find the approximation for the quantity that I mentioned, it's useful to provide two kinds of expressions for this quantity as a transition amplitude on a replicated Hilbert space. Okay, so for most things that I'll do, I'll be interested in the exponential of Sn. So just this e to the minus n minus 1 Sn. Which is the trace of the reduced density matrix to some power. So I can, if I use the path integral representation for this time evolution operator U, then I get a path integral representation for this whole expression which can be written down on which involves n contours of forward evolution and n contours of backward time evolution. Okay, and roughly the initial state, so I haven't written down in detail what the initial and final states are for this path integral, but roughly the initial state is determined by the initial density matrix rho 0. And the final boundary condition is determined by the pattern of traces that you take in A and A bar in this expression. Okay, so you have some boundary conditions, but inside the path integral, what you have is this space, which involves a sum of S for all forward trajectories and minus S for all backward trajectories. Okay, so one thing that we can notice about this expression immediately is that if we just set if we set the fields on each forward evolution to be equal to the fields on some backward evolution, not necessarily the same one, then we'll find that the phase in this path integral just vanishes. Okay, so this was a nice observation which was made in this paper. So that means that at late times, you might expect that for general configurations, these phases would be very widely oscillating with time because you're just taking a sum of phases which are very large. But for this special set of configurations where you set phi I equal to phi prime of sigma I for some element of the permutation group, these would just be stationary with time. So heuristically, it's natural to imagine that these configurations might dominate in some sense at late times, or at least in some kind of late time average. Okay, but if we just put this condition directly into the path integral, then it's easy to see that we just get a divergent answer. So this is not a good thing to do in itself, but it gives us some intuition for the fact that that it would be nice to be able to project onto a set of configurations which involve these permutations. Okay. So in the next few steps, I'm going to try to make this intuition more precise and develop something more systematic. Okay. So I have to, in order to do this, I have to introduce a lot of notation. So please ask me if you get confused at some point about what some of these symbols are supposed to represent. So in general, I'm going to represent permutations in Sn with symbols like sigma and tau. And then two special cases of such permutations which I'll use will be the identity permutation, which just sends every element to itself, which I'll call E, and a permutation called eta. So I'm using a cycle notation to represent this, but this is a permutation with a single cycle, and it just sends n to n minus 1, n minus 1 to n minus 2, and so on until 1, and it sends 1 to n. Okay? So then for any operator O acting on one copy of the Hilbert space, and any permutation sigma in Sn, I can define a state associated with this operator and permutation on 2n copies of the Hilbert space. Okay, so to define what this state is, let me first assume that I have some basis I for one copy of the Hilbert space. Then I can represent the state O sigma in a basis like this for 2n copies of the Hilbert space. And the overlap of this state with this basis element is given by a product of n copies, a product of n matrix elements of O. And essentially which of these states I take the matrix element between depends on what permutation sigma I have. Okay, so in a particular case of O equal to the identity operator, I just get delta functions between the states in the different copies like this. And I'll just represent these with the permutation, so I won't add the operator label in these cases. So to get some intuition for what what defining these states does for us, suppose that we took the overlap of the state OE with the permutation labeled by, with the state labeled by just E. Okay, so in this case, we end up getting a trace of O to the power of n. If instead we took the overlap of the same state with the permutation eta, then we would first multiply O by itself n times and then take the trace. Okay, so in this way, you can get different kinds of patterns of taking traces by taking overlaps with different etas. And of course, we can also define, if we have some subsystem of the full system, then we can use a basis for that subsystem to define states O sigma within that. Okay, so now using all of this notation, we can write this expression for the exponential of the nth Renyi entropy in this form, where, like in the path integral representation, the initial state is just determined by rho 0. And then you have a time evolution operator, which is like a tensor product of forward and backward time evolutions for each of the copies. And the final state is determined by the pattern of traces. So you can see that in the region A, you get the permutation eta. And this kind of makes sense. You can roughly understand why this makes sense, because eta corresponded to just taking the trace after multiplying all the copies, which is what we do in the subsystem A in this expression. And similarly, in the region A bar, you just get the permutation E. Okay, so this is the expression that we've ended up with, and this is what we'll use for all of our further manipulations. So do you have any questions at this point? Okay. Great. So, so to do what I mentioned before, which is to find some kind of regularized way of projecting onto the permutation states, what we do is we consider the set of states spanned by these I alpha sigma for all possible sigma. Okay. So this I alpha is whatever equilibrium density matrix we chose to be associated with our initial state. So we define this projector. It doesn't really matter. I just wrote down this expression to give you something explicit that you could see. It doesn't really matter what this G sigma tau and this other factor is in here. The reason that they're included is just that these different states are not exactly orthogonal to each other. So to make the projector square to itself, you need to have some additional things. But anyway, you can define a projector onto the set of states, which I'll call P alpha. And then you can always decompose the identity operator on 2n copies of the Hilbert space as a sum of P alpha and its orthogonal projector, which I'll call Q. So then I can just substitute the identity operator on either side of this U times U dagger to the n in this expression. So that's all I've done here. But then from the fact that I alpha is invariant under the action of U, you also find that acting with this time evolution on P alpha on either side leaves P alpha invariant. So as a result of this expression just becomes a sum of two parts. One part which is not time dependent anymore, which involves just projecting onto the permutations inside the transition amplitude. And you have some time dependent part, which is the rest of the time evolution. So that is the part involving these Qs. And our proposal is that at late times and in systems with large Hilbert space dimension, to find the late time values of the entanglement entropies, we can just ignore this contribution from Z and Q. So we just keep the contribution, which involves projecting onto these permutations. Okay, so that is the main sort of set of physical inputs that go into our approximation. Okay, so then it's possible to, so this is just the expression from the previous slide written down. This is our approximation. And then in the case where the effective Hilbert space dimension is very large, we can just simplify this expression further. And we find that it simplifies to a sum of terms which depend on so a sum of all possible elements of the permutation group. And the expression Zn A of tau has a very simple representation, which is just the inner product of this final state governed by the pattern of traces with I alpha tau. Okay, so in particular, note that in this expression, the dependence on this specific initial state rho 0 is dropped out, and this expression is written only in terms of this equilibrium density matrix I alpha. Okay. At the same time, it's not just the nth Renyi entropy of I alpha, because that corresponds to the tau equal to identity term in this. So all of the other terms are giving us some further information. Okay. Great. So this is the expression that we'll be working with everywhere. Are there any questions about, any further questions about the steps up to here?
A question?
Yeah.
How unique is this choice of I alpha giving an initial state?
Yeah, that's a good question. So we have some self-consistency conditions that we need to impose in this expression. For example, from requiring Zn of A to be equal to 1, we get a certain self-consistency condition. So we haven't, yeah, we haven't studied that question in a lot of detail, but it would be a good question to understand more. But there are definitely some constraints on what I alpha is appropriate to choose. So and I'll also be talking about another criterion for whether this approximation is valid or not in a couple of slides. So that will probably give some further constraints for checking whether if you choose a certain I alpha, it works or not.
And hopefully, if it's not unique, different choices will not give different physical answers.
Yeah, that would also be an important thing to check.
Thanks.
Yeah. Great. So, I seem to be failing to go to the next slide. Just a second. Okay. Anyway, okay. So, are you still able to see most of? Does the screen still look big enough? I'm not sure why the full screen didn't work anymore.
Yeah, only the title is cut off as far as I can tell, so that's fine.
Okay, perfect. Great. So let me provide some more justification for this expression. So the exact expression, as you recall, was just written as in this form, which involves this transition amplitude. And one thing that we can do is just average over all unitary time evolution operators U with the uniform measure. Okay, and in this case, we find that we just get our equilibrium approximation with I alpha equal to the identity operator. Okay. So this was an observation that was also made in this paper by Zhou and Nahu. Then, of course, we can also look at the variance under this average. So we can just compare the square of the average to the average of the square. And in this case, we find that this is much smaller than our estimate for the average itself in the limit of large dimension. So this means that if we choose some random time evolution operator, which doesn't have to respect any constraints from energy conservation or anything like that, then we would in general expect that with a very high probability, it can just be replaced with this set of permutation states involving the identity operator. Okay. But then for other choices of row equilibrium, so in more restricted setups where you have some Hamiltonian time evolution with energy conservation constraints, we don't really have a similar average that we can do over all relevant time evolution operators. Okay, so in this case, we have to come up with some other type of criterion. For this, it's useful to discuss a slightly more general picture, where so far I've told you about this approximation for the Renyi entropies. But of course, we can just do this for any quantity that we can write as a transition amplitude on some 2Q copies of the Hilbert space. So anything which can be written as a transition amplitude where the initial state is rho 0e, and the final state can be anything depending on what the quantity f is. We can define the equilibrium approximation by just replacing this u times u to the u dagger to the q with p alpha. And if we can do this for the quantity f, then f squared is also of exactly this form. So we can also define an equilibrium approximation for f squared. And then we can compare what we get from the equilibrium approximation for f squared and what we get by just squaring the approximation for f. And for this approximation to be self-consistent, we should find that this quantity is much smaller than our actual estimate for the square. Okay. And indeed, for the Renyi entropies, we can show that when the effective Hilbert space dimension is large, then this variant or this difference is indeed very small. Okay, and we do seem to find that in other situations also this criterion matches our physical expectations. For example, this quantity, which is just the expectation value of some operator O in the state, can again be expressed in this general form, just with Q equal to 1. And if we just apply the same equilibrium approximation, then we find that it's given by its expectation value in the equilibrium density matrix. But we expect that this should not work in cases where the operator is very large. In particular, if it worked for just all operators in the system, then we know that that's a problem, because that would essentially imply that our state is just equal to the equilibrium state, which is not true. And indeed, we find that this, that if we assume that O has support only on some subsystem A, then we find that this self-consistency criterion is met when dA is much smaller than dA bar, but not otherwise. Okay. So this is another justification. And then in response to Eugen's question, this would be another thing that would be important to check if we're choosing some I alpha to make sure that it actually works. Okay, cool. So, with this, we can also slightly extend the calculation that I mentioned on the previous slide to show that if we directly find the equilibrium approximation for Zna to the power of n, then it's very close to just taking the nth power of the equilibrium approximation for n. And this gives us some confidence that if we just analytically continue, then indeed the equilibrium approximation value of the nth Renyi entropy is what we would expect. It's just given by taking the log of the approximation for the exponential. Okay, and similarly, we can analytically continue in a different way to get an approximation for the von Neumann entropy using the approximation for ZNP. All right. Okay, cool. So now, now that we've developed the approximation and we've justified it with the self-consistency criterion, let me talk a little bit about some universal mathematical structures that emerge from this. So like I said, you can just approximate this Zn of A as a sum of terms governed by the different permutations. And each of these terms can be given a diagrammatic representation. So this means that if we, so for all of these diagrams, the exterior structure of the diagram is just governed by this pattern of traces. And then they're connected internally in different ways depending on what tau is. Okay, so these are just 3 different examples. Here I've used the cycle notation again to represent this permutation. So this is a permutation with 4 cycles, and it sends 1 to 4, 4 to 1, and so on. Okay, so then another general feature of this diagrammatic representation is that so you'll see that each of these diagrams has some number of dashed loops and some number of solid loops. And the number of dashed loops is just equal to the number of cycles in the permutation tau. Okay, so 4 in this case, and n in this case, and 1 in this case. Yeah, maybe I said that backwards. Anyway, so I think, yeah, maybe this is backwards actually. So maybe it should be the number of solid loops is equal to the number of permutations in tau. Anyway, so then you can find that that if you want to find some overall scaling behavior of this expression Zna of tau, then you find that involves some number of powers of dA, which is equal to the number of cycles in eta inverse tau, and some number of powers of dA bar, which is equal to the number of permutation, the number of cycles in the permutation tau. Okay, and we can also show that for any tau, the sum of the number of cycles in these 2 permutations is less than or equal to n plus 1. And this is a condition which is saturated for a certain subset of permutations, which we will call non-crossing permutations. And these are precisely the ones which are associated with these planar diagrams. Okay, and the permutations which are associated with non-planar diagrams like these are all suppressed and don't satisfy this this condition which saturates this. Okay. And then another convenient way of representing our expression for each tau is a path integral representation. So if we write this expression from the previous slide a little more explicitly, then we find that each of these terms corresponding to each tau involve n factors of matrix elements of I alpha. So if I alpha has some path integral representation, for example, in the canonical ensemble, we know that there is a Euclidean path integral representation that's associated with it. Then we'll have some path integral with some initial and final states. And each final state will be associated with some initial state. But because of the structure of this expression, we'll identify the initial and final states in different ways in the regions A and A bar. So in the region, for example, if we consider the permutation corresponding to tau equal to E, then we'll just cyclically identify the states in the region A, and in the region A bar, we'll just identify each initial state with the corresponding final state. Okay, and you have all possible kinds of other patterns coming from these other permutations tau in this whole sum. So overall, what we've done is that we've replaced, like in the course of this approximation with our final expression, what we've done is that we originally had a Lorentzian path integral on 2n copies of the system. And we've approximated it with a late time expression, which involves several Euclidean path integrals on n copies of the system. And you get one such expression for each element of the permutation group. Okay. All right. So this was the upshot of what we've done in the path integral language. So let me just talk about some universal physical consequences of this final expression. Okay. So one thing that we can immediately check is just using these properties of inner products on 2n copies of the Hilbert space, is that we can write down this expression in a way that's manifestly symmetric between A and A bar. Okay. So it immediately satisfies this constraint from unitarity that the entanglement entropy of the region A should be equal to that of A bar. And then using this general scaling behavior with the dimensions of A and A bar that I mentioned, we can also find what the dominant contributions should be in various regimes. So in the case where dA is much smaller than dA bar, we find that the largest contribution will be from the largest power of dA, which comes from the tau equal to E term out of all of these terms. And this just ends up being equal to the thermodynamic entropy of this equilibrium density matrix in the region A. Okay, and that is something that we would expect quite generally on physical grounds. But if dA bar is much smaller than dA, then the tau equal to eta term should dominate out of all of these. That would be the term which has the largest power of dA bar in this expression. Sorry, the largest power of dA in this expression. And so that would be equal to the thermodynamic entropy of this equilibrium density matrix in the region A bar rather than A. Okay. So that shows that in this case, where one of the subsystems is much smaller than the other, we just get the expected generalization of Page's result, which is that we get the minimum of the equilibrium values of the entanglement entropies in these regions A and A bar. Okay, and with this expression, because it's the same for all n, we can also just easily analytically continue it to find that the value of the von Neumann entropy is just given by the minimum of the von Neumann entropies for A and A bar in the equilibrium state. Okay, and then in the case where dA and dA bar are both large and comparable, then we need to consider some additional contributions. So then you can't isolate one particular term in this whole sum which dominates. And instead, in this case, from what we discussed before, we need the largest possible sum of these two powers. And that just ends up being n plus 1. So we need to consider all contributions from all possible non-crossing permutations or planar diagrams. Okay. So just one example of the structure that emerges from considering this sum over all planar diagrams, we can consider in the infinite temperature case, where essentially we end up with a sum of all possible combinations of powers of dA and dA bar which add up to n plus 1. But if the power of dA bar is k, then the coefficient of this term will be something called a Narayana number, or the number of non-crossing partitions of n objects with k blocks. So this is so this interpretation of the coefficient just comes directly from our picture of picking out the planar diagrams from that whole diagrammatic expansion that we had. Okay, and so the simplest terms in this sum are just the ones which give us the values of log dA and log dA bar in the limits where one of the subsystems is much smaller than the other. But then in the intermediate regime, you need to consider all of these terms. Okay. And by analytic continuation of this expression, we can also find an expression for the von Neumann entropy, which just agrees with Page's result. But one nice thing about deriving this from the equilibrium approximation is that in principle, we know what part of the expression we've left out for any specific time evolution, which is the ZQ part. So in principle, we can systematically develop corrections to it from the result at very late times by studying the ZQ contribution. Okay. And then we can also apply this to the canonical and microcanonical ensembles. So one nice thing is that we're now able to use this structure to find universal results which apply for pure states that equilibrate to these ensembles, which are applicable to any quantum many-body system. Okay, so we found these universal expressions, and then they have some general features, which include the fact that if you consider the case where dA is much smaller than dA bar, then these ensembles will give the same result if you appropriately associate the temperature with the energy in the microcanonical ensemble. But they will give different results when dA over dA bar is finite. So in these cases, we can distinguish between states which equilibrate to the microcanonical and canonical ensembles. And then we can check that our results here agree with some previous results which involved averages over special sets of states. So we can check that our microcanonical ensemble result agrees with a previous average over a certain set of states called ergodic bipartition states studied in this paper. We can check that our canonical ensemble result agrees with a previous average over canonical thermal pure states, which were a special set of states corresponding to some temperature beta. But one nice thing is that unlike Page's calculation, these averages over special sets of states couldn't really be seen as averages over time evolution operators. So it's nice to be able to see how these expressions emerge from as approximations to the time evolved expressions, and also to see how they come from a common structure. Okay, so those were some universal facts that I wanted to point out. Also, we can assume that, so far we've assumed that we have the full system which equilibrates after some finite amount of time, which we call TS. But in general, we would expect that if we have some uncompact system, which has local interactions, then there doesn't really exist a finite time scale of this type, okay? But in such systems, we can still assume that some subregions of finite size can thermalize locally. So we considered a specific, very simple example of this, where we considered a 1+1 dimensional system, and we assumed that it had some sharp light cone. So that means that if I have some region A, time t, then the region in the past which could have affected this region is just this region J of A, which is accessible within its light cone. And then you can argue, and you can have a very precise argument for this in a case with a circuit model, that to find the nth entanglement entropy of the region A, you can essentially just ignore the evolution in the region J bar when the initial state is a product state or some short range entangled state. Okay, so then in a highly chaotic system, we can just make the simplest possible assumption, which is that we have local equilibration in the full region J of A around A at time t. Okay, so if we just treat this J of A as the full system and apply the equilibrium approximation, then we find this very universally observed structure that you find that initially the entanglement entropy grows linearly, and then it saturates at some value, and there's some prefactor determined by the equilibrium entropy density. Okay, so So it would be nice to develop a more sophisticated version of this, which considers cases without maximally efficient local equilibration. But we can see how this general structure can come from from this equilibrium approximation when it's modified for local systems. Okay. Great. So those were some general facts, and now I want to talk a little bit briefly about some applications to the black hole information loss paradox. Okay. So like I mentioned before, the key to showing that black holes don't destroy information despite the fact that they look thermal is that the entanglement entropy of the black hole is equal to the entanglement entropy of the radiation at all times. So this is a question which falls very nicely into the type of thing that we've been discussing so far. The paradox in this came from the fact that a calculation in semi-classical gravity by Hawking predicted that at late times, the entanglement entropy of the radiation becomes much larger than that of the black hole. Okay, so roughly the picture looks like this. The entanglement entropy of the radiation just continues to increase for all time, while the entanglement entropy of the black hole is decreasing. So at these late times, it's much larger than the entanglement entropy of the black hole. Okay, and for many years, it was believed that maybe Hawking's information loss paradox can only be resolved if we have some techniques in non-perturbative quantum gravity, which can deal with this situation. But the remarkable thing about many recent works which have come out is that they provided a semi-classical prescription, and it involves some new ingredients, but it was sufficient to get a unitary result for the black hole entropy. Okay, and it only involves semi-classical gravity. So there's a path integral version of this calculation. So let me just outline in a very cartoon picture what this calculation involves. Okay, so if we were just calculating S2 of the radiation, then from everything we've discussed so far, we know that we wouldn't have to consider two replicas of the system. Hawking's information loss paradox comes from doing a gravitational path integral calculation where the black holes in these two replicas are disconnected from each other. Okay, so doing the gravitational path integral essentially involves just integrating over all possible metrics with this kind of topology where these two systems are disconnected from each other. Okay, so if you just see what comes out of this calculation, then you find that indeed at late times, the entanglement entropy of the radiation is much larger than that of the black hole. But then a nice thing that was found in these papers in some specific models, which can be summed up in this way, is that if we want to find a unitary result, that S2 of B is equal to that of S2 of R, then we need to include replica wormholes. So we need to include topologies where these two copies of the black hole are actually connected to each other. Okay. So it was found that if you include these replica wormholes, this was introduced as a sort of ad hoc prescription, but it was found that you do always get a unitary result in the models that were considered in these papers. But then some things that were not really well understood was what is the fundamental reason for including such replica wormholes, and why do they always seem to give a unitary result? And what we did in our paper is that we essentially showed that applying the equilibrium approximation to these setups gives a very precise derivation of the replica wormholes for calculating SN. So in particular, in the models which were used in these papers that I mentioned, we were able to precisely recover their prescription. And the central idea here is that these unconventional geometries for in the path integral of SNR come from considering the terms other than the identity permutation in our Euclidean path integral representation. Okay. And this is nice because now that we have a derivation in these particular models, we also know how to apply the equilibrium approximation in principle to other kinds of black hole models. And this can always give precise prescriptions for when and how replica wormholes should be included. And the reason for the result being unitary comes from very general grounds from our earlier argument that that expression is just manifestly invariant under interchanging A and A bar. Okay. And then one further thing that we were able to clarify using the equilibrium approximation in this problem had to do with this question. So in this paper, it was noted that including replica wormhole contributions leads to some results which resemble ensemble averages. For example, if you calculate the square of this matrix element of the reduced density matrix of rho r, and you include the wormhole contributions, then it seems like the calculation for the square of this quantity is not equal to the product of the individual calculations. Okay, so this would kind of make sense, for example, if both calculations involved calculating an average of these quantities. For instance, if you were calculating an average over an ensemble of theories. So this suggested the question of whether somehow semi-classical gravity is intrinsically computing an ensemble average rather than an exact result. And whether it's always, in these holographic theories, whether semi-classical, at least in the semi-classical approximation, if it's always dual to an ensemble of theories rather than a single theory. But we essentially showed that we can derive all of these results in a single theory by applying the equilibrium approximation to it. And so this can be done in a system with a fixed Hamiltonian, and there's no ensemble of theories that's needed to explain this. It just happens to be that we're calculating the late time approximation to these quantities. Okay, and in particular, this lack of factorization of this quantity just comes from using the Euclidean path integral as an approximation to the exact Lorentzian path integral. So it enters even before we use semi-classical gravity to actually compute the Euclidean path integral. Okay, so it was nice that we were able to use these kinds of tools which came from very general quantum many-body systems in order to clarify this question about gravity and ensemble averages. Okay, so do I technically have 5 minutes remaining at this point?
Sure, yeah, 5 minutes sounds good.
Okay, great. So then I'm gonna just use the remaining time to talk a little bit about how to understand this picture from an operator evolution perspective. Right, so in general, we expect that the kinds of systems which equilibrate are chaotic. And there's a very general picture of how operators behave under Heisenberg evolution in chaotic systems. So it's expected that if we start with an operator which initially has support in some very small subsystem, for instance, in a spin chain, we could imagine an operator which just has support on one side, then we expect that its support should grow with time. Okay, so in particular, in the spin chain case, we can imagine that it's growing along some light cone in this form. For example, many nice universal properties that result from this kind of operator growth have been found, such as the decay of outer time ordered correlators, and so on. In this paper with Hong, we found that there is another process that needs to be considered to understand the internal structure as the operator grows a little better. So within the growing support of the operator, it has some probability of becoming equal to the identity in any given region. So in this local case, for example, where the endpoints of the operators are growing, this time-evolved operator O of t will have some part O1 of t, which will be equal to the identity in any given region A. Okay, and we refer to the presence of this O1 of t part in O of t, which is trivial in A, as void formation from the operator O in the region A. Okay, and it's important to understand what kind of probability there is for this process to occur in order to understand various forms of entanglement growth in various systems. Okay, so in general, we expect that this probability should be small at late times in a chaotic system, since the support of operators tends to grow in chaotic systems. But this small but finite probability has several important consequences. So in particular, the result that we'll be most interested in today will be how it ensures the unitarity of entanglement growth. But we can show that it also is essentially, this kind of process is responsible for generating multipartite entanglement between disjoint regions. And it can also explain the differences in patterns of entanglement growth with time between local, integrable, and chaotic systems. Okay, so these were some other applications that we discussed in our earlier paper. But today I'm mostly just going to tell you a little bit about how this is related to ensuring to understanding this equilibration consistent with unitarity. Okay. So to do this, the argument is very simple. You just start with your initial density matrix for your pure state, and you decompose it as a sum of two parts. Okay. So for the trace of this to be 1, if you separate out the traceless part, rho hat, then this whole thing has to be a sum of I over d plus rho hat. Okay. So then if we assume that the probability of void formation, the probability, if we assume that because of the picture of operator growth, rho hat will in general become very large, and we just neglect the probability that it forms a void in any finite region such as A bar at times much greater than the scrambling time, then when we find the reduced density matrix rho A, the only thing that contributes is the identity. So we just find that the reduced density matrix is maximally mixed. And we just get this result that Sn of A has to be equal to log dA. So in particular, this is an expression that's not invariant under the interchange of A and A bar, and seems to violate the requirement for unitarity. Okay, whereas what we wanted in the infinite temperature case was that we should find that the entanglement entropy of A and the entanglement entropy of A bar should both be equal to the minimum of the logs of these two, of the dimensions of these two regions. Okay, so essentially, in order to include the contributions from these other permutations in our equilibrium approximation picture, which gave us a unitary result, from the operator growth perspective, what we need to include is the probability that this traceless part of the initial density matrix forms a void in the region A bar. Okay, and then we can make this a little more precise. So in particular, we can find some condition on the weight of this rho 1 part, which has a void in A bar. So we find that it has to satisfy a certain condition in order to get this result for equilibration to infinite temperature in a unitary system. And in fact, we find that this condition on the weight of this part is actually satisfied for any initial operator O, if we consider a chaotic local random unitary circuit. Okay, yeah, so this is nice because somehow we're able to show that in this infinite temperature case, it seems like this kind of equilibration in a unitary system is a result of a general property of operator growth. And we call this kind of form of the void formation probability the random void distribution. Okay, great. So yeah, so just to sum up, some kinds of future things that we would like to do would be to try to apply this method to other kinds of observables, such as other types of entanglement measures like negativity, because all of them can be written in that form where the equilibrium approximation can be applied. And it would be nice to systematically understand some corrections to it, and also to understand if we can understand the finite temperature case in terms of a universal property of operator growth like we did in the infinite temperature case. Great, so that's all I wanted to talk about.
Thank you very much. Maybe I'll stop the recording here and then we can, we have time